Our main goal in this lecture will be to show that power series, or more generally series of continuous functions, may converge to continuous functions. To this end, let's just recall quickly what we know about regular series. So the regular series would converge if it satisfies something that we call the Cauchy criterion. And the Cauchy criterion was related to the fact that sequences of partial sums of a series were themselves Cauchy sequences. And we used Cauchy sequences in this case because we didn't know the limit of the sequence of partial sums. So rather than showing that the sequence converges, we wanted to demonstrate that the sequence of partial sums is Cauchy, and then the two notions of Cauchiness and convergence coincide. So it's okay to show that a sequence is Cauchy, that proves convergence. So something similar we should expect for series of functions. So a series of functions converges if a sum of, and I'm speaking in very general terms now, we'll make this more precise in a few minutes. A series of functions converges if, again, the sequence of partial sums converges. And once again, it would be difficult to show that the sequence of partial sum converges. Instead, you'd rather show that your sequence of partial sums is a Cauchy sequence. Now, to prove continuity of the sum of the power series, we will need to rely on the notion of uniform convergence, right? Because that's a notion which ensured that the sequence of continuous functions converges to a continuous function. And so in this case, then we have to recast the notion of uniform convergence again in the Cauchy sense, because once again, we would not know what the limit of the partial sequence of partial sums is. So we need to recast uniform convergence in a uniform Cauchy way, and then demonstrate that if a sequence of functions is uniformly Cauchy, then it converges uniformly. And so without further ado, let's try to give a definition of a uniformly Cauchy sequence. We would say that a sequence Fn so a sequence of functions defined on some interval I is uniformly Cauchy on I if and so the definition is going to be very similar to the definition of Cauchy for regular sequences, right? What was that definition? That given epsilon, there is capital N, such that if n and m are bigger than capital N, then Sn minus Sm was less than epsilon. So the distance between Sn and Sm is less than epsilon. So in this case, everything is the same, except that now we're dealing with functions, so we need to use a definition of a distance between functions, and that, per what we did before, is a supremum of a difference between two functions on an interval. So if for every epsilon greater than 0, there is a capital N in R, such that M and N both bigger than capital N, that this should imply that a supremum x in I of Fn of x minus fm of x, that this is less than epsilon. So the definition, as I said, is exactly the same as what it was before, except that because we're now dealing with sequences of functions, the distance is not just absolute value of the difference, but it's a primum of the difference between values of the function on your interval. Other than that, everything is exactly the same. And so then we want to prove the same theorem as we proved originally for regular sequences. And that will be this theorem. A sequence of functions fn is uniformly Cauchy on the interval I if and only if fn converges uniformly to some function f defined on I. And so we need to prove this in two directions. Going forward, so let's suppose that fn is uniformly Cauchy, right? Is uniformly Cauchy on I. And we want to prove convergence, right? Again, I want to emphasize that I'm not really doing much new in the sense that before exactly the same result was true for just regular sequences. Okay, so if fn is uniformly Cauchy on I, then what do we need to do? We need to show what the limiting function function f is, and then prove that fn converges to f uniformly on I. Right? So we have to follow two steps. Okay, step number one. In fact, before I do the step number 1 and 2, let's recall one more thing. I think this is something that we proved last time, that a sequence of functions converges uniformly to f on I if, so what was it? If for every epsilon greater than 0, two f's. For every epsilon greater than 0, there exists an n in R such that n bigger than capital N. This would imply that the supremum x in I of fn of x minus f of x, that this quantity is less than epsilon. Or, we proved this before, equivalently, we can express a last statement in the following way. If n is bigger than capital N, then fn of x minus f of x, absolute value, that this is less than epsilon for every x and I. Right, that is what we showed last time, and there is nothing really nothing difficult about it, right? Because if a supremum of the difference fn minus f is less than epsilon, that means that fn of x minus f of x is less than that number for all x, right? And equivalently, if fn minus f is less than epsilon for every x and I, then by just slightly more complicated argument, it follows that actually the supremum is also less than epsilon. Anyhow, similarly to this, we can rephrase the property, or let's say the uniform Cauchy property as follows. So let's see, uniform Cauchy again required the supremum here, right? So the equivalent definition that I can give is this, that instead of saying that the supremum of the absolute value of the difference is less than epsilon, because supremum is less than epsilon, I can simply claim that the difference is less than epsilon for every x in I. So for every epsilon greater than 0, there is an n in R such that n, m are both bigger than capital N, that this would imply that the absolute value of fn of x minus fm of x, that this is less than epsilon for all x in I. Right? So that would be the definition of uniform Cauchiness that I'm going to use in the proof of this theorem. Okay, so step number 1. As advertised, I need to show that the function f, the limiting function f, exists. Okay, so we already supposed that Fn is uniformly Cauchy, right? And from the definition that the way we just wrote it, definition of uniform Cauchiness that I have written here, what we see is this, that if I fix x, right, then it still follows that for every capital N, there exists little n and m bigger than there exists a capital N, such that whenever little n and m are bigger than capital N, then the difference between Fn of x and Fm of x is less than epsilon. So if x is fixed, I never would know that Fn of x and Fm of x came from a function, right? And I'm simply looking at the sequence of numbers, Fn of x and Fm of x. And from what we have written here, that sequence actually is a Cauchy sequence, right? So from the definition of a uniformly Cauchy, it follows that for every x and I, if epsilon is greater than 0, there is a capital N in R such that m and n bigger than capital N. This implies that Fn of x minus Fm of x is less than epsilon. That is the sequence, or for a fixed x in I, the sequence Fn of x per what I have just written here. That sequence of n of x is a Cauchy sequence of numbers. Right, and therefore, by what we know from before, any Cauchy sequence of numbers converges. So Fn of x converges. And I'm going to call a limit of Fn of x f of x. Right? So therefore the limit n goes to infinity of Fn of x is equal to f of x. A double, the column here means that I'm simply defining f at x as a limit of Fn of x. Okay? And so this now defines my f of x at all x and I. Right? Once again, what am I doing? I'm just fixing x because the sequence is uniformly Cauchy, then it is Cauchy at every individual x. It's a sequence, Cauchy sequence of numbers for every individual x. And therefore, as a Cauchy sequence of numbers, it converges to some limit. And I'm calling this limit f of x. And so that means that the limit of Fn of x at every x is f of x. And so we conclude from this that that new function that I found fn, that the new function that I found, it is a limit of my sequence of functions, and the limit is valid at every individual x, so that means that fn goes to f pointwise. On I. Okay, so we found the function f to which our function sequence of functions fn converges pointwise on I. And so now step 2. Show that fn converges to f now uniformly on I. Just one point that I want to emphasize again, right? We talked about this last time. If the sequence of functions can converge uniformly and can converge pointwise, uniform convergence is stronger. If a sequence converges uniformly, then it must converge pointwise. So there is nothing else to prove in this case. But if a sequence of functions converges pointwise, it may or may not converge uniform. So we have to do some significant extra work to actually prove that convergence in this case is not just pointwise, but also uniform. All right, so what have we got? So given an epsilon greater than 0, again, as usual, I'm just rewriting the definition of a limit a zillion times. So given an epsilon greater than 0, because fn is uniformly Cauchy, there exists a capital N in R such that if M and N are both bigger than capital N, then Fn of x, right, again, I can either use a supremum or just state that Fn of x minus Fm of x, absolute value of x, absolute value of that. In principle, I'm typically writing less than epsilon, but in this case, I'm going to say epsilon over 2, and it will be clear in a moment why am I using epsilon over 2 instead of epsilon. And that is going to be true as long as, in fact, for any x in I, right? Okay, so that is fine. So this is equivalent to saying the following, that Fn of x minus Fm of x, that this is less than epsilon over 2 and greater than minus epsilon over 2 if M and N are greater than capital N and x is in I, right? All right, so we're going to look at this, and now let's see what else we can say. Okay, so therefore, let's look at it from another point of view. So for every x and I, now let's examine this relationship here now. So if I take M and N bigger than some capital N, then I'm guaranteed that fn of x minus fm of x is going to be less than epsilon over 2 and greater than minus epsilon over 2. Because now this is true for every m and n bigger than capital N, I'm going to fix n, and I'm going to let m go to infinity. Right? As m goes to infinity, the inequality is still valid, right? So for every x in I, and some fixed n bigger than capital N, we have that if I take a limit, so if I know that fn of x minus fm of x is bigger than minus epsilon over 2 and less than epsilon over 2, if I take a limit of the expression inside as m goes to infinity, nothing is happening to fn of x, and fm of x, as we know, goes to f of x, right? So minus epsilon over 2, then the limit, oops, and m goes to infinity, fn of x minus fm of x. This should be less, well, I don't know that it is less yet. So that is my next question. Do the inequalities retain their sign or not? What can happen in the limit? If each individual term of my sequence is less than epsilon over 2, then as I take a limit, as we all know, right? So if I take a limit, maybe the sequence is less than epsilon over 2, it's monotone increasing. It's entirely possible that it will, if for example it is monotone increasing, it is entirely possible that the limit is going to be epsilon over 2. But it cannot be anything bigger than epsilon over 2. We proved that back in advanced calc 1. So that means that the limit should be less or equal than epsilon over 2 and greater or equal than minus epsilon over 2, right? And then I can actually add one more statement to this set of inequalities. If the limit is less or equal than epsilon over 2, then certainly it's less than epsilon. And if it is bigger and equal than minus epsilon over 2, it's certainly bigger than minus epsilon, right? And so therefore, again, for every x in I and a fixed n in capital N, I have that minus epsilon is less. Now, what is the limit of fn of x, again, when m goes to infinity? Fn of x is a constant, right? And x is being held fixed, so that is just f of x. Fn of x, right? It doesn't change, it's the same thing. And fm of x, the limit is f of x, so minus f of x, and that whole thing is less than epsilon, right? And this is true for every fixed x, right? So for every x. And for my fixed n that is bigger than capital N, right? But I can fix any n bigger than capital N, so that means that this statement actually is true for every x in I and every n bigger than capital N. So x and I. And so therefore, what have we found? So therefore, we can rewrite this as, in fact, this is an equivalent statement, absolute value of fn of x minus f of x is less than epsilon for every x in I and n bigger than capital N. But that means that I'm done, right? Because if this is true, right? If for every epsilon I can find capital N such that if n is bigger than capital N, then f n of x minus f of x is less than epsilon for every x in I. That means that my sequence fn converges uniformly. Let me actually add that here. So we conclude that fn goes to f uniformly on I. All right, and so now we need to go in the opposite direction. That's another part of the proof. And this one should go in exactly the same way as it did for just Cauchy sequences of numbers. So suppose fn converges to f uniformly on I. So therefore, for any epsilon greater than 0, there exists an n in R such that n bigger than capital N would imply that absolute value of fn of x minus f of x is going to be less than epsilon, but again, in this case, I'm going to say less than epsilon over 2, and this should be true for every x in x. X in I. Okay? So now let's suppose that n and m are both bigger than capital N, right? So then I'm going to compute fn of x minus fm of x, right? And again, I want to show that this difference is less than epsilon, right? And what you do is you do this telescopic sum argument that we have already seen before. I can write fn of x minus fm of x as fn of x minus f of x plus f of x minus fm of x. Right? Because I don't know that fn minus fm is small, but I certainly know from here that fn minus f is small, right? Okay, and then I can use a triangle inequality. This is going to be less or equal than fn of x minus f of x plus fm of x minus f of x, right? So that's a triangle inequality. And what do I know? Because I assume that n and m are bigger than capital N over here, right? Then it follows that each of these absolute values is going to be less than epsilon over 2, which is equal to epsilon. Again, all of this is true for every x and I. Right, and therefore this fits the definition of a uniformly Cauchy, so therefore the function sequence of functions fn is uniformly Cauchy on I. And now the proof is complete. Okay, so then I'm going to continue in the next installment of this lecture.